Okay, and I have to share my screen. Yes. So first of all, good evening, all of you, and welcome back in the ongoing series. And today, the method which we want to discuss here is symplectic integrator for Hamiltonian systems. Okay, and this method is very useful if you are studying or working on Hamiltonian system of equations. Oh, okay. So this is one of the numerical method used to approximate the solutions of Hamiltonian systems, which describe the dynamics of conservative system in classical mechanics. These integrators are designed to preserve the symplectic structure of Hamiltonian system. They conserve volume in phase space and maintain the fundamental properties of the system such as energy conservation. And in the Hamiltonian system, the state of the system is described by a set of generalized coordinate q and their conjugate momenta p, and the dynamic are governed by Hamilton's equation or the governing Hamilton's equations, which are given at this place dq upon dt is equal to curl h upon curl p, and dp upon dt will be equal to minus curl h upon curl q, where h is the function of q and p. This is the Hamiltonian function representing the total energy of the system. In this lecture, I am not deriving these equations, just I want to explain how we can find out the solution of these Hamiltonian system of equations. Okay, so there are some steps which we have to follow, and there are three methods. One by one we will discuss, and what are the algos, how we can establish the equations, everything will be discussed here. Okay, so just if you need to establish these equations, I will provide the content. Okay, if I will discuss how we can establish these equations and then how we can solve, then a lot of time is required, and during this lecture we are not able to cover. But I think I consider that you are familiar about these two equations. If you are not, then you must go through the file. Okay, I will provide you later. I will provide you the complete derivation of these equations. Okay, so here h is the function of q and p is known as Hamiltonian function, and representing the total energy of the system. So here we will use symplectic integrator, which is favored for Hamiltonian system because they tend to exhibit better long-term stability and energy conservation compared to non-symplectic integrators like a standard Ankata method or the others. So this method is preferred, which is symplectic integrators. And there are some two more methods which can be easily implemented as we will use this symplectic integrator. So there is a little difference between these two. So here how we can use the algo, and here you can see the solution of the above equations will be q and p. Okay, just 1 minute. Here is 1 minute, please. Epic pen. Okay, not working. So here I have to open in the other way, and now it is fine. Yes. Okay. Yes. So here we have these two system of equations, and we want to find out the solution of these equations. So first we need the solution of these equations will be the function of q and p. Okay. So we need to write here the programming to solve the system of equations. So here h is the function, which is the Hamiltonian function handle, which we need to write. Okay, and then observe these equations, which type of functions are involved in these two equations, and according to these, all we need argument in the function. So the file which we will save in the name of symplectic integrator with the name of the method, and then here is dhdq, this one we need this derivative. Then we need also dh upon dp, which is involved in the first equation. Q naught and p naught, these are the initial values when t is 0, corresponding to the given initial conditions of this system of equations. Dt is the step size, and these are the number of steps. Okay, so as we discussed in the old previous methods, and initial conditions, the function, and then the all type of here we have two type of partial derivative. So both are required to find out the solution of these equations. Okay, so we will calculate all these values, and all these will be argument for this method. Number one. After that, we will execute and we will establish the equations. C at this place. So also Q and P, these are the outputs which are in the function, and finally when we will simplify. Okay, so we will start from the given initial conditions. When t is 0, we have Q and P. These are the initial arguments. Okay, so here we need to update the value, and how we can do. P will be updated P minus delta P minus dt, and we have is partial derivative of dh dq or del h upon del q, and also we know that h is function of q and p. So from this place, we will update the value of P using partial derivative. And similarly, we need to update the value of Q. So Q will be equal to Q plus dt and dH upon dP. Also here, H is function of Q and P. Okay, so this is del H upon del P. And these two both are easily can be updated by following the above equations. So this is the main function which we need to write or the approach to find out the solution of these two equations. Okay. After that, suppose we have one example, and we wanted to find out the solution. Okay. So suppose that h we have is h is this function. We have h is we are doing this solution for taking one example, and h is some function like this type. Okay, and the value of omega we have is 1 angular frequency, or we can change according to our problem. Now, if we need the corresponding values which are the argument of the above function which we write, so we need to calculate or compute the value of del h upon del q from this equation. So when you will take the partial derivative of this equation with respect to q, p will be constant, and ultimately when you will take the partial derivative with respect to q, okay, so this will be omega square q. So 2q into 0.5 will become only q, and the other part is constant. And similarly, the value of dh upon dp or del h del p will be equal to only p. Since when you will take the partial derivative of the above equation with respect to p, so q will be constant and we have only p. So these are the two equations. After that, we need to initialize the initial conditions. Just 1 minute. Dear participant, please keep muted your mic. Okay. So then after what we do, we need to initialize the conditions, and suppose that the initial conditions we are given q naught is equal to 1 when t is 0 and p0 is 1. So these are the initial conditions, and step size we have is dt is equal to 0.1, and the number of steps we are choosing at this place 100. After that, we need to pass these values through the function which we establish, and you can see at this place. So this is the performance of integration. So this is the our output function is function of p and q, which are the final values. Okay, and we call the function at this place, and these are the corresponding argument of this function. Okay, so the same function which we establish will be called at this place, and then we display the final state. So here display the final value q, and we needed to convert the numerical value in the string. Okay, so final q will be corresponding to this q final value, and final p will be equal to, we have the final value of p. So when we will use this method, this algo, we can have easily the values of p and q. So the same code I have written in the MATLAB, and we can easily execute the same. So here is this is our program, and yes, so here you can see, just 1 minute, I have to close all these files so I can avoid the confusion. So the example one, and here is, okay, and these are the numerical value. Okay, correct. So here is the same function which we discuss right now, and with the name of symplectic integrator, and these are the corresponding argument. Okay, and all these are the parameters, their descriptions are given at this place, and here the same steps, the initial conditions for p and q, and then we are using here the for loop, okay, to update the values of p and q. So and at this place, so this is our program, and we need to save. Then after, we need the numerical values, and the same statements we are using here. We are choosing the value of omega as 1, okay, and this is the h function by using function handle, and then after, we need the partial derivative of both with respect to h, with respect to p and with respect to q, according to this requirement. Okay, so h will pass through at this place, dh and dq, these are also required, dh dp also is required. Okay, so both are partial derivative with respect to p and with respect to q, and then we have the initial values whatever we are given, and the step size and dt both depends upon our choice. Okay, and after that we will call the function. All the argument, the corresponding values will pass through this function, and ultimately when we will execute, we will have the values, final values of p and q, which will be stored at this place. Okay, so this function will ultimately solve all the equations corresponding to the given initial conditions, okay, and their partial derivatives which we defined at this place. So then after at this place, we will display the result, and when you will execute, you can use also here CLC and clear is used. Fine. So when you will execute, you can see these are the final values of q as well as that of p. So this is in this way we can easily use this approach to find out the solutions of a system of Hamiltonian equations. Any doubt in this discussion? If you have any question, please let me know if you have any question. And this is a very simple approach. Just you need how you can establish these equations. Yes, please.
No, sir, this fine, sir.
No? Okay. So then after, we have one more example which I choose here. Yes, no, and CLC. Once again, I have to come back. Is there any numerical value? Okay, and now example number 2. In the example number 2, we have the results and this file, this file. Okay, 1 minute, please. I have to arrange in the one pattern. This not required. Okay, this is the final result, file 1, and this is the function, this is the gradient, leopard, leapfrog, and 1, 2, 3, and 4. 1, 2, 3, 4. Okay, this one, and yes. Okay, so now the method which we want to discuss, that is leapfrog integrator, and this method is also similar type as we discuss first one. Okay, the leapfrog integrator is a method for numerically integrating ordinary differential equations. It is commonly used in the Hamiltonian system due to its symplectic nature. It preserves the symplectic structure of the phase space. So in the place, if sometime required, we can use this algo also. And the approach is, this is the algo. Q dot is equal to curl h upon curl p, and p dot is equal to, we have minus curl h upon curl q. So p and q are the same. Q represents the generalized position and P is the momenta. Okay, so leapfrog integrator update the positions and momenta alternately in the discrete time step, and these are the steps which this algo will follow. P n plus 1 by 2 is equal to Pn minus delta T upon 2 curl h upon curl qn. Okay, and qn plus 1 will be equal to qn plus delta t curl h upon curl p pn plus 1 by 2. And then after pn plus 1 will be equal to pn plus 1 by 2 minus delta t upon 2 curl h upon curl qn plus 1. And delta t is the time step. So just we need to follow these equations. These equations are important to implement this algo, okay, which is familiar with the name of leapfrog, but the implementation is same as we discussed the previous one. So here, if we suppose that you have this equation, HQP is equal to 1 by 2 P square plus 1 by 2 Q square. Okay, and if you want to use this method, so here we need to write the function qp leapfrog underscore integrator q note p note dt steps. Okay, and q will be zeros steps 1. So as you know, the length of the both must be equal, and similarly we have the p zeros, and you know the zero vector, all the element will be 0, and these are the initial conditions. Q1 means Q naught and P1 means P naught. So 1 here is index, and then after the above equations, these are the above 3 equations which we discussed. Okay, we need to convert in the MATLAB syntax. So here you can see these are the syntax of the above equations, 3 equations. So first we need to create this function, okay, leapfrog integration, and then after we can use the same. So for the MATLAB implementation, come to MATLAB. So here we have leapfrog pq dt, where pq and dt is the step size, as you know. And also we need Hamiltonian equation. This is the Hamiltonian equation, okay, and function. This is the Hamiltonian function, and we write in the form of a user-defined function, okay, and along with we need gradient only for q, okay. So the gradient is defined as dqh omega square product q, the partial derivative with respect to q only. Okay. Then after we have this is the given Hamiltonian function. This is the our algo, and we need gradient at this place. Okay, that's why we have to create a new function in the name of gradient, which is defined at this place. Now for the numerical result, we have to call only this method and see. So here is the example which we can use to find out the solution. Okay, so the example is that we are taking the initial value q0 is 1 and p0 is 1, step size 0.1, and the time steps are 100. Okay, and then integrate for the same. Okay, so what we do, what is the meaning of this one? Q and p, these are the initial values, and when we will use 1 to time steps, and time steps are 100. Okay, so all these will at a place we will call the function. So this will compute all the values corresponding to all the steps. Okay, so f print function we are using here, f print f. So here is step D. The value of q will be print at a place. The step size 1, 2, 3, and so on. Then the values of q corresponding will be printed. Then we have the p, and these are the argument of the function h, and after computing the value of h, this will be printed. So when you will execute to see what we have the outcome in command window. Just 1 minute, I want to scroll up. Yes, so when we will execute this sequence of statement, okay, and when you will execute, you can see in the command window. Okay, and here is, yes, so this is the step 1. The value of q is this one, and the value of p is this, and corresponding to when we have q and p, the value of h is this one. For the step 2, the value of q is this one, and that of p is we have minus 0.198503, and that of h we have is this value. So this will compute all the values up to, see, the number of steps we have is 100. Okay, so this is the last value. So we choose at the place 100 steps, and corresponding to every step we have the value of p, we have the value of q, and corresponding to the Hamilton function we have the same value. So in this way you can easily compute these values. Okay, so these methods which we discuss now are specifically defined for Hamiltonian system of equations or governing equations, and you can easily use for different type of problems. Okay, and also if you are similar type of problems or other system of equations, we can find uh, some other applications also. Okay, but this will take some time. If you have a similar type of problem, and also the methods which we are using here, not only for these Hamiltonian equations. Okay, these methods are also can be used for the other problems, but depend upon which type of problem we want to solve. Okay, but here I do not check the applications in other system of problems about these methods. Just like we discussed now, leapfrog integrator. Okay, and the first method, and also we have, there is one more method. There is one more method. Here is given. Here is, yeah, you can see these two methods. These two methods are also can be used, can be implemented for this Hamiltonian system of equations, okay, which are associated with the simple harmonic oscillator. Okay, but also these methods can be used for the other problems. I want to say, if you are able to use these two methods for Hamiltonian system of equations, there will be some more applications for different type of problems. Okay, so there are two more algos I clearly defined in the script file. Here is the second one. Okay, so you will try this one by writing your own code. Okay, this is similar to as we discussed for leapfrog integrator. So only these two equations are required, and on the basis of these two equations you can easily write the code and you can find the solutions of the problem. Okay, and also at this place example is given, and to make easy I insert here the syntax of MATLAB code so that you can easily try yourself. Okay, but remember, when you will scroll down and see, just we are converting the equations in the MATLAB syntax. Very simple. Not required any more function as we do for the leapfrog. Okay, here we need to find out the gradient also, but in this method not required. Simply you can use this function to find out the solution. Okay, so this is about this method. And for this one more method is there. There is one more method. Just 1 minute. 1 minute, please. Okay, this algo I don't know whether I prepare the code or not. Just 1 minute, please. First, let me know if there is any doubt about this discussion. If you have, we discuss now 3 methods. If you have any doubt, any question, please let me know.
Hello.
Yes, please.
Yes, sir. I
Hello.
have a one query where
Yes,
we
please.
calculate it, then the value of p. Yes, sir. Whenever we calculate it, and the value of p is nearer to zero, minus 0 point something in 94th step. In that case, value of h is too high.
Just 1 minute. Yes.
So we can see the value at 94th step. Q is
94th.
minus 0.99 something, and the P is yes, sir. This one.
Yeah.
H is
Also
so high.
here,
After getting to the point,
here is also.
no, sir. This is the all value is 0.499999. A value of H is. We can see the value of H and
Value of
value of
H, yes,
P is
yes.
yeah. This is the largest value to compare to the other all.
This is
So
the
if
largest
we
value.
try to for the P is 0, this is the peak point of simultaneous equation.
Actually, these calculations are based on our inputs.
Yes, sir.
Okay, so depends upon the step size. We can do some more experiment. We can do some more experiment by changing the value of a Q note or the value of a P note, and then you can change the step size. You can
Step size. Okay, sir. Okay, sir. I
yes,
got
yes.
it. Got it. Okay.
Okay,
Thank you.
so when you will change these initial values, because these results completely depend upon our input, our initial conditions. Okay, then the time step and the number of steps. Okay, so here we have the number of
Okay,
steps.
sir.
And
Thank you, sir. I got
so
it. Thank you.
okay, sir. So corresponding to these values will return. If you make changes, if you make here some more change, you can find. Suppose this is 0.5 and this is also 0.5. And when you will re-execute and see the values again completely change. Okay, so all these will depend upon our initial values. Now we have new values. All the values are new.
I got it. I've got rid of this doubt.
Thank you.
Okay. Thank you.
Thank you, sir. Thank you. Any more question, please? So I hope you will try some more examples for this Hamiltonian system of equations. Okay. And one method you will try yourself, but syntax is given there. Tomorrow we will join at the same time. And if you have more query, please don't hesitate. You can ask from me. And now our sessions will be continuously tomorrow and Monday also. I have we have holiday. I think Monday also I will take this class so that we can finish, we can complete all the lectures which we have proposed in this ongoing course. Okay, I want to complete all the lectures during the end of this month, and I hope that this will be easily covered. Okay, but the thing is, I'm repeating again and again, you must try yourself also. When you will write the code yourself, you will have some challenge, and when you will find out the solution, you have more learning. If you make one mistake, you will familiar with some more problems, and you can easily manage the syntax, how you can convert the syntax, and how you can establish the sequence of statement. You will be able to write your own self to manage the arguments, the system of equations, and how you can convert the given problem into the most of the methods what are in the form of iterative. So iteration we need to apply. So if you are able to convert all the equations in the iteration form, then you can easily implement MATLAB to find out the solutions of these equations. And I hope that you are working in this direction. If you are not doing, you must do in this direction. Okay. And any more query from your side if you have?
Yes, sir.
Gangtak and Pan. Yes.
Greetings, sir.
Good evening. Good evening.
Good evening, sir. How is work today, sir?
Yeah, I'm today is fine.
Okay.
Today is fine. Now I feel in comfort zone because after coming back, everything mismanaged.
Yes, sir. Yeah, actually, sir, we have to appreciate you for your effort so far.
Thank you.
Yes. Actually, your effort has made a lot of changes, most especially in me and the way I
Mm.
view most of these things. And I am really appreciating you for that, sir.
Thank
And
you.
I think you actually deserve a place in the acknowledgement of my thesis because the knowledge I've gained so far have actually helped me a lot. But for proper learning, I discovered something that watching through videos alone makes it the rate of learning to be very slow. But if I have your script file now and I must not always need light I must not always need energy to learn. I can just print them, keep them on my own when I'm free. I can just look at it, then have another problem, and then try to write it in a different way other than what I'm saying. So I think by that, it will deepen learning because like me, I study better when I have the hard copy of what I'm studying in front of me. So most of the materials I find so important, I print them and then study them carefully. Then see how I could not think on how to even go about it better. So I don't know how you can help us in this case.
What do you expect from me?
Okay, sir. I want to plead that if you can
Pardon?
down your script files, the script files
Script
of the
file.
lessons.
Okay, you are not able to get the script file, right? You
Yes,
are from
sir.
Nigeria.
Yes, sir.
Okay. You are studying in India or at your place?
At my place.
Okay, don't worry. Please, you can contact me after the session. You will register there. I will pay for you. Okay.
Okay, sir.
Then you will get everything.
So thank you, sir. Thank you
Any more?
very much.
Okay.
Thank you, sir. Okay.
Hello,
Yeah.
sir. Good
Yeah.
evening.
Yes, please.
Yeah. I'm also suffering from same problem. Already I investigated, but not able to download all this file.
Okay. Okay.
Yeah.
Okay. You are also facing the same problem.
Yeah.
You can um, join the hand together.
Okay. But how? But how?
Uh, you can use a single email address. Both should have a username and password.
Yes, yes,
Share
yes.
share your username password together.
Okay.
Yeah. So you can both enjoy the lectures. You can download the script file, everything.
Okay, sir.
Okay.
Mm.